Hello, and welcome to the Firevoxel tutorials. In this tutorial, we will show you how to perform image co-registration for four-dimensional images. This operation is often used to perform motion correction for dynamic images. Firevoxel's 4D co-registration tool is an extension of the autofocus method for 3D image co-registration. For details on autofocus, please review 3D co-registration first. We will use a set of three-dimensional MR images of mouse brain acquired after the administration of manganese contrast agent during 9 imaging sessions on consecutive days. The images have the same matrix and voxel size, and a test tube with a contrast agent solution is placed next to the animal for signal intensity calibration. We also drew a rough region of interest around the brain to help co-register this image. We will switch the view to coronal and scroll through the dynamic points. We can also use the Play 4D function to display this dataset as a movie. We can see that there's a substantial mismatch in the mouse brain position from image to image. Our goal is to minimize this mismatch using the 4D co-registration tool. To use this command, on the main menu, select Register Autofocus Motion Correction 4D. This opens the Autofocus 4D co-registration dialog. In the top portion of this dialog, there's an option to use the target ROI. If there is an ROI layer present in the document, this option is checked by default. If no ROI layer is detected, the option will be grayed out. As with the 3D co-registration, Firevoxel's 4D co-registration can be made faster by using a target ROI drawn on the target image around the part that needs to be co-registered. The target ROI restricts the computation of transform functions to the organ of interest and helps to speed up co-registration. Co-registration can be performed without the target ROI, but will be more time-consuming. Next, we will select the co-registration scheme. Firevoxel offers two schemes, serial and radial. With serial scheme, one time point is selected as the starting image, and the next time point is co-registered to it. The target is then shifted to the next time point, and co-registration is repeated. The process is iterated separately towards the first and last time points in the dataset. With radial co-registration, one image serves as the target to which all other images are co-registered. The radial scheme is the simplest and most common, and we will use it selecting the first dynamic image as the target. We will then select the similarity measure from the drop-down menu and pick Mutual Info. As in the 3D co-registration, this setting selects the method for the similarity measure calculation between the source and target images. Now we will configure the autofocus parameters. These are the initial values used by Firevoxel to begin fine-tuning, which is an iterative search for the best transform. First, we will select the subsample of 2 for using every other point to speed up the similarity measure computation. For transformations, we will keep the maximum translations at their default settings of 20 mm in each direction. This means that Firevoxel will restart the search 20 by 20 by 20 equal to 8,000 times. We will set the other 3 autofocus parameters for rotations to 0. In this case, the same mouse is being imaged at each time point, and therefore 3D rigid transform with 6 degrees of freedom is the most appropriate model. Therefore, we will select a rigid transform for the fine-tune stage. For output interpolation, we will pick Sync 2, which is the most appropriate setting for MRI. Now, click OK to proceed with co-registration. After a minute or two, the co-registered image is returned in a new, automatically created layer labeled _registered, added on top of the base layer. The resulting image is a 4-dimensional dataset with the same dimensions as the original. The dynamic point with the largest misalignment, as determined by the similarity measure, is displayed first. If we compare the registered and base datasets, we will see that the first image remains unchanged. This is because we used the radial scheme, and the first image was the target to which all other images were aligned. Scrolling through the images, we can see that the motion from image to image has been reduced, and the mouse brain is now fully contained inside the target ROI. Note that the result reflects some rotations, even though we set to 0 the autofocus rotation grid of initial values. This occurs because of the fine-tune step. The registered image also shows some degree of smoothing. It is particularly noticeable here because of the low resolution of this dataset. Now let's go back to the base image and scroll back to the first dynamic point. For greater accuracy, we can select a larger set of autofocus grid points. Select the rotation angles of 10 degrees and the grid of 5. Also, increase the power to 3. This transformation is going to take a longer time to process. After processing is complete, the result is returned in a new layer. Again, the dynamic image first shown to the viewer is the one with the maximum misalignment. We can examine the quality of the registration by scrolling through the time points. To improve the registration accuracy, the user can increase the power and autofocus gridding. Note, however, that these settings are likely to increase the processing time. This concludes this tutorial on the Firevoxel's 4D co-registration using autofocus. To learn more, please visit our website. Thank you.